Greetings all, this is Mr. Mays coming to you once again through the digital modalities. Welcome to today. And today, what today will be marked by is part one. Oh goodness me. Is part one of everybody's favorite, binomial distributions. Now, obviously, it is presumptuous of me to suggest that binomial distributions are everybody's favorite, but they're probably some people's favorite. They're certainly close to my favorite, although how could anyone pick amid the brilliant distributions of statistics? So if you'll join me really quickly, we're going to be looking at slide 4.4, which is our first set of slides on binomial distributions, and you're going to walk through it with me starting on slide 7. Okay, and slide 7 gives us kind of some ideas of the types of questions that binomial distributions look at. So for example, toss a coin 5 times. What is the probability you will get 5 heads, right? And there are 2 other examples there. One with spinning a roulette, and the third with a sample of 100 babies. Obviously, babies are on the mind for me because my little Miles has recently been born and is giggling and laughing at everything, right? What you'll note, though, on slide 8 is I set out for you an acronym called BINS. And BINS is a perfect way to understand if something should be binomial or not. Because we're reaching a point in the year where we start having to run tests on what kind of distribution we're using and when we should apply certain rules. So BINS is how we know if we're going to use a binomial distribution. One, we need a binary. This can be an imposed binary or a binary that's inherent. An inherent binary would be something like a coin, where you only have 2 options, heads or tails, right? But there are other kinds of binaries, right? Like if I use dice, I could go and say odd or even. And if my question says you are looking at either odds or evens, I have created a binary. So that's the first thing. So the second thing we need is independence, right? And this is important because every single binomial distribution will have an expected probability, a probability of X, and that has to be consistent for every single thing that happens. So, for example, on the slide 7 that I was talking about, if you flip a coin 5 times, each coin flip, as we've already learned, does not impact future coin flips. There's always that 50-50 chance of probability of getting heads, right? So we need to be sure that there is independence. And we'll talk about a few ways that we can note in a question if independence is present. But aside from those examples, we need to have it said in the problem, treat these events as if they're independent. The third thing is we need a finite number of trials. So for some distributions, like as we'll soon learn in geometric distributions, we don't need a finite number. We can say, what are the odds that I get this result after 5 tries, 10 tries, 30 tries? But with binomial distributions, I need to know my endpoint. I need to actually know the breadth of the entire distribution before I can then go and say, well, it's a binomial distribution and let's make X, Y, and Z assumptions about it. So we need a finite n number of trials. And we call that lowercase n. That's the variable. And then finally, successes. Okay, we need a probability of success. This kind of ties in with independence, right? We need a probability of success that is the same for all, right? Same for all trials. So with a coin, it's 50%, 0.5. But with other iterations, we'll see different ways in which this shows up, right? So I'm going to go ahead and I'm just going to highlight my BINS real quick, make sure we know that that's our acronym. If you're like me and you're not big on acronyms, well, just remember, what do you need for a binomial distribution? Well, you need a binary of some kind, an on-off button, a yes or no, that has a version of success. That version of success has to be consistent across all trials, and I have to have that probability, and I need to know the total number of trials. Finally, there needs to be a certain amount of independence. It needs to be clear to me that each choice doesn't change the odds of the next choice, or doesn't give more information about the odds of the next choice. Okay, beautiful, beautiful, beautiful. Let's move on to slide 9. Here we go through how to check for independence. So the 2 main things you'll note here are, there are really 3 ways, normally. 1, it says it. Wow, how exciting, Mr. Mays. Yes, sometimes it just says, treat these like they're independent. 2, we see with replacement. What does with replacement mean? You should know this inside out and backwards by now, but that means, for example, if we draw a card, with replacement, the second time we draw a card, we have replaced the first card we drew, so it's like starting over fresh. The third thing we need, of course, is randomly sampled is another way we know that events are independent, right? You randomly sample a bunch of elk, as we'll soon see in one of our problems, or you randomly sample penguins, or you randomly sample any part of the population. And what random sampling does is it eliminates the notion of dependence between our variables. Why? We've randomly sampled them. There's no connection between them. All right, those are our sets to determine independence for now. And I want to give you a little side note, okay? This is our little real-world side note. The real world with Mr. Maze. What is the side note? Well, look, it's a secret, really. A lot of things, right, are dependent, and we don't know. We don't know the degree to which they're independent. We're unsure about it. So there's a little rule in the real world, which is that you can treat events as independent, even if there could be some dependencies. Now, again, it's not for things where they're outright dependencies, but where there could be some overlapping dependencies. We can treat them as independent, even if it's without replacement, if we use what's called the rule, the 10% rule. And all that says is that our sample that we're looking at for our binomial distribution, right? Our sample n size cannot, and this is weird, this is like the opposite of the law of large numbers, cannot be larger than 10% of the true population. Cannot be larger than 10% of the true population. So what does this mean? Well, what this means is sometimes you can treat events that are not truly independent, that have certain dependencies or that we're not entirely sure about, as if they are independent. And we can afford to do this on a larger scale when the sample we're looking at is not larger than 10% of the population. And the reason why is we've taken a small enough subset of the population that the dependencies are not going to heavily impact. That bias is not going to heavily impact our sample. And if we were to go and run further tests, we would then determine what those dependencies are and work around them. But this is just an example of something that we quite often do when we are working through statistical problems. And I told you in class that this happens a lot in environmental science and biology situations where we look at endemic populations and we make assumptions that there are not dependencies when there might in fact be just a real world side note, right? It's like dipping your toe into the pool. Okay, if you flip forward, there are classwork problems you should work through. Is it or is it not binomial? And you can see that I have some examples here. Mr. Miller's class, Mr. Mays making free throws, ages, die cast. We can all go through, and we've gone through these answers in class, and in the next slideshow, there will be solutions for them. Alrighty, let's roll on to slide number 11, where we talk about the notion of how we notate a binomial distribution. You will remember that when we notated a normal distribution way back when, but you should not forget this, we did n, and then we did mean, comma, standard deviation, right? On the other hand, when we notate a binomial distribution, we use a similar framework, except we do b instead of n, because it's binomial, not normal. And then we do n, comma, p, where, of course, n is our number of trials. We've gone over that. I don't know why I said of course. Of course, n is our number of trials. And p is our probability, which should be consistent because the events are independent. Okay. The last thing to note is x, just like before, where x is like a data point. X is also our number of successes, right? Right. X also interchangeable with k, and in a lot of our notations we say probability of like x equaling k, or probability that x is greater than k, or probability that x is less than or equal to k. And we're going to go through these in the next set of video notes to get a feel for different versions of this notation. But all this is saying is, what are the odds that a certain number of successes occur, or that more than a certain number of successes occur, or less than or equal to a certain number of successes occur? And there are a bunch of different versions of this. Less than or equal to, greater than or equal to, less than, and greater than, etc. But x is just the number of successes that we have. That's how we notate that. All right. Now we move on to slide 12. There are two main functions on our beautiful TI-84 calculator. So if you would swap yours out real quickly, the love of your life is in your hands. What do? Well, we're going to learn how to use Binomial PDF and Binomial CDF. And I'll make it wonderfully simple for you. Oh, I wrote PDF twice. Here's how I remember the difference between these. Binomial PDF, the P stands for probability. I like to remember it as a point because it looks for the specific point. What are the odds? Probability that X equals a particular point K. That's Binomial PDF. Binomial CDF, the C stands for cumulative. Right? Cumulative, very important. What does cumulative mean? Well, as we all know, cumulative means adding up from the start up to wherever you are at. And just like in real life, when you're taking a test and someone says the test is cumulative, that means it covers from the start all the way up to where you are at. At the end of the year, that's going from the start to the end. But it needn't be that. It will be from the start all the way to our success number. From 0 successes up to whatever number of successes we've set. Okay. Hopefully you will not mix these up. So that means Binomial CDF is used for all the other versions. X is greater than, X is less than, X is less than or equal to, and X is greater than or equal to. Any version of those probabilities with K, right? All of those will be Binomial CDF, cumulative. Binomial PDF, a single point. Binomial CDF, cumulative, okay? And you can see the directions are up there on your screen. All you have to do is go to distribution, which is where we've been going for the normal curve as well. And then from distribution, you either go to either A or B, which is either Binomial PDF or Binomial CDF. And there are three things you have to plug in, no matter which one you're doing. You have N, you have P, and you have K. K, of course, is number of successes. I'll put number of checks, right? Number of successes. P is the probability as a decimal. And N is the number of trials total that you did. So in class, we looked at an elk problem. I almost said a reindeer problem. An elk problem where we were given a probability of success that was 0.44 of survival. We wanted to know the odds that 4 elk would survive. That's successes. And there were 7 elk in total. And you just plugged those in and you would get your odds of exactly 4 elk surviving. Okay. On the other hand, cumulative is when we want to know what are the odds that at most 4 elk survive. Or what are the odds that more than 4 elk survive. Things of this nature. And next set of slideshow presentations, we'll go in more detail on that. But I want to give you a brief visual of each of these, right? So for Binomial PDF, let's imagine our binomial curve. Remember that our binomial curve is not a normal curve. It may look like one, but in reality, it's skewed. And it's skewed about our probability, whatever that probability is. So wherever that probability sits, that will be where our mode, our mean sits, understandably, right? Because that's where our averaged events will show up. And we'll learn that next time when we multiply n, the total number of trials, by p, the probability of success. That is our mean for our binomial distribution, which makes sense, right? It's just the total number of options times the probability of success. It's what we've been using all of our lives before coming to this brilliant statistics class to delve further into knowledge, right? So, if you will, what Binomial PDF does is it just gives us the highlighted, and I'm really trying to just highlight this line right, ooh, goodness, right here. Whatever you plug in, this, and actually it shouldn't say P of X here, whatever X is, our number of successes that we plug in, right? It's only giving us the probability of that particular discrete value. And one thing I want to throw on your radar is that we are talking specifically about discrete values right now when we are talking about binomial distributions, right? Success and failure, number of heads, number of tails. We are dealing with whole number values here. And that will come into play an enormous amount when we look at different ways of solving for binomial distribution functions, right? So binom PDF, looking at a particular set of distributions. So it is actually in and of itself a bin, and that bin sits at whatever your number of successes was. If it's 4, that is the probability of exactly 4 underneath a curve that holds 3 and 2 and 1 and 0 and 5 and 6 and 7 and 8 all the way up to the total number of proportionate values available. On the other hand, binom CDF, looking at our curve, gives us the cumulative set of values going up to our number of successes that we plug in. So this is X, our number of successes, right? Binom CDF goes from 0 specifically all the way up to the right. Now, what it cannot do is do a right-tailed test. It will always do a left-tailed test, right? Go over back to this. It will always do a left-tailed test. It will never do a right-tailed test. So if we want to take this right section, well, we would take our value for this and do 1 minus whatever we got for our probability that we found in binom CDF. I've got my little crayon pencil here. All right. And then on slide 13 and 14, you have 2 problems, both of which we did in the classwork/homework, and you can go through each one of those problems. I went over the solutions with you in class. They are also available up on the 4.5 probability notes. So what I'd like you to do is go through and try to do all of the A, B, C, D, and E sections of this 3.26 chickenpox problem, and then go ahead to slides 4.5 and run through the solutions, and I will be there with another set of video notes to guide you further through this brilliancy. But let's finally wrap on up. I'll miss you, of course, but just remember the following things. 1, we've learned when to use binom CDF versus binom PDF. We now have a visual binom CDF going all the way from 0, only from 0, from the start, all the way up to whatever success rate we plug in, including that success rate itself. Okay? If we want to find the opposite end of that spectrum, we do 1 minus. If we want to find the opposite end of the spectrum, but including the value we've stopped at, we actually go 1 lower, right? Because we're always using discrete values here. And we'll go in more detail about that later, but we use binom CDF when we want cumulative functions and binom PDF when we want specific values, when we're dealing with these discrete. Oh my gosh, wait, you almost, I'm sure in your head you were like, Mr. Mays, you spelled discrete wrong. You forgot the S. Let's slide that S in. Look at that slithery S. We got it covered. Discrete. I ain't no English teacher. All right. I've also given you a sneak peek as to the kinds of probabilities that we do with binom CDF versus the ones that we do for binom PDF. More to come on that later. We've looked at the things that we need for a binomial distribution. We need a total number of trials. We need a probability that remains constant across all of those trials, which means they are independent. We also need to have a number of successes, right? We've learned how to enumerate our binomial distribution, capital B, and then in parentheses, total number of trials, comma, probability overall, which should make sense. We've stated that in the real world, we can't always know if dependency is or is not there, so we can treat events as independent using the 10% rule, which is to say that if our sample size is not larger than 10% of the true population of something, like an animal, and we do like a really low number, this happens in environmental science all the time, well, we find ourselves in a fortunate position where we just treat those events as independent because it is literally negligible the degree to which tiny dependencies will impact our sample size. Otherwise, though, we either need to have a problem say that the thing is independent, say with replacement, or say that it is randomly sampled. These are our signs that independence has arrived. And we check for that alongside 3 other things. 1, that there is a binary, an on-off button, a success failure that we can set, that we have a finite number of trials, and that we have a probability of success that's consistent, along with the fact that it is independent. And that is all that you must know to feel comfortable with binomial distributions. You should feel solid on this. I am so proud of you and so thankful from the bottom of my heart that I get to teach you every single day. Thank you for being my students. This is Mr. Mays, signing off.